Good morning, everyone. It's our great honor to introduce Yingfan Chen, a third-year PhD student from the Department of Computer Science at UIUC, to present his latest work on coding agent with LLM. He is a PhD student from, he earned his master's degree from NUS and his bachelor degree from Huazhong University of Science and Technology. Yingfan, you have the floor now.
Okay, thanks, Ziyi. So thanks everyone for being here. So today I'm going to introduce the RCA Copilot, which is to automatically collect the incident-related information in the cloud and also leverage the large language model to do the root cause analysis for the cloud incidents. So this is a joint work with Microsoft, University of Illinois Urbana-Champaign, Peking University, Huazhong University of Science and Technology, and National University of Singapore. So let's start. So okay, as we all know, the cloud is becoming more and more popular, and so as its incidents. So those incidents have a huge impact on those big tech companies and also the customer user experience. So the incidents exposed to the customers may bring us a very bad user experience, like the 503, 404, such kind of error codes, and also those big tech companies may also lose a lot of money due to the incidents. So when an incident comes, there is a very important procedure named incident root cause analysis, basically the RCA. So the root cause analysis try to triage the incident to the corresponding service team. Maybe there are some experts or corresponding engineers who are responsible for the incidents, so they can fix and mitigate the incidents. And also the root cause analysis can help solve the incident fundamentally because we know the real root cause. So in that case, we can improve the service reliability. And also RCA can prevent a similar incidents happen again in the future. So in this motivating example, as we can see that the root cause is a hardware problem. For example, CPU temperature is very high, or the machine is down, etc. in the cloud infrastructures. But the ramification brought from this incident root cause could have a lot of ramifications here. Like storage service may have some partitions not loaded, and also the network service may be down for some time, and also some VMs cannot be launched, or some low login success rate for the SQL service. So the engineers who are responsible for these incidents may feel very, anxious, or they are just feel like finding a needle in a haystack, since there are a lot of ramifications in this cloud world. So to win this war in full, actually we have some helpers. As we know that we have logs, we have traces, we have metrics, we have all of these data sources from different targets or different parts of the cloud to help us to debug, right? So in Microsoft, basically Microsoft has an incident management system. So basically the engineers will update those kind of informations in this thread or in this ticket to continue working on it until the incident is finished or incident is mitigated. However, actually, those kind of monitoring information for the on-call engineers, basically OCEs, may feel either difficult to collect those information, or those kind of information may be overwhelming for them. So when I say difficult to collect, I mean those kind of information may be imprecise. So basically, the information may be too less for the engineers to debug. And when I say overwhelming, I'm referring to like the volume of this kind of multimodal or heterogeneous information may be too large. So the on-call engineers may easily feel lost, get lost. So actually, there is a kind of another helper named the troubleshooting guide. Basically, troubleshooting guide is a kind of document that the on-call engineers can read or follow during the debugging of the incidents or during the mitigation of the incident. So basically, the engineers will follow this troubleshooting guide step by step to see like how to solve the incidents, how to mitigate those incidents. However, as a document, we may imagine that it have many limitations. First, it requires the engineers to manually gather data. So as for example, in the second step of this first troubleshooting guide, the engineers need to click into the dashboard to see the exceptions in the exception table to do the further debugging, right? So this kind of manual, work is non-trivial. And also as a document, it may easily becomes outdated if there is nobody maintaining, this kind of document. And also these documents may contain insufficient details, like some common checks like a disk check or CPU check may easily be ignored by these documents. So they are not very user-friendly. And more importantly, it can generate information that spends OCE's long time to interpret and analyze the results. So even if we have this troubleshooting guide, the on-call engineers may also feel lost. So it also have other drawbacks or limitations. So actually, this is very contradictory to the instant incident root cause analysis, which is our ultimate goal, right? So what should we do? So in our work, we try to solve these limitations by using our framework, RCA Copilot. We try to solve the first three limitations by using the automatic incident information collection module of the RCA Copilot. And also we try to leverage the larger model to help us to interpret and analyze the incident related information. Okay, so I will go through these two modules later. So in that case, we can achieve the incident root cause analysis. So the contribution of this work is that first we have done a study of the 1-year incidents from a very large email service within Microsoft, and we derived the 3 insights, and those insights help us to design the RCA Copilot. And we propose the RCA Copilot, which is an automated end-to-end solution for the cloud incident root cause analysis. It is efficient, and also it integrates a large model to predict the incident root cause categories, also with the explanations. And we have deployed the RCA Copilot within Microsoft. Okay, so the goal of the RCA Copilot is all about the automation. We want the RCA Copilot to automatically collect those diagnostic information from multiple data sources, like the logs, metrics, or data, and the traces from multiple, data from multiple parts of the, clouds. And also we want to achieve an automation that interprets and analyzes the collected incident-related information and predict the root cause. So that's a goal of our design. So this is the architecture. So as you can see that we have 2 stages. One is the collection stage. The other is the prediction stage. So in the collection stage, basically one incoming incident will be mapped to a corresponding incident handler. And those handlers will be executed with some actions. So those actions will automatically collect the information from the cloud. And those information collected from the first stage will be fed into the second prediction stage. So in the prediction stage, we will try to summarize those incidents, and we will try to find the similar incidents from our previous database of the incidents. And also last step is to do a root cause prediction. And we will feed the final results to the OCEs, the on-call engineers, to help them to analyze the incidents. Okay. So let's talk about the collection stage first. So basically, the intuition behind the collection stage is that, okay, collecting diagnostic information is just like performing a decision tree, right? So when you read a troubleshooting guide, so we'll finish step 1, you can jump to the step 4, and then step 6, etc. So basically, it is just a decision tree. So whenever a condition is satisfied, you go to the next step, right? You go to the left node or you go to the right node. So we want to RCA Copilot to automatically, execute the predefined incident handlers when incident comes. So for each handler, actually, it is composed of 3 types of actions. One is a scope switching action, the other is query action, and the last one is mitigation action. So the scope switching action is very necessary. It's very necessary and important for the RCA Copilot. Why? Because during the workflow of the RCA Copilot or incident handlers, the scope may be changed. So at one time, you just apply your handler to a DAG here, which is a database available group, right, or forest, or even larger. But later, when you figure out, okay, I need to narrow down my scope, I need to focus on a single machine or a smaller bunch of machine, then we need a scope switching action to do this kind of action to narrow it down or to make it bigger if we feel the bug may happen in other places. So that's a scope switching action. And for the query action, basically it can query data from different sources and output the result as a key value pair table. So query action basically is is kind of a collection. It's kind of a collection action. It can be hooked to a specific script, like a PowerShell script, to collect the different data from different data sources. And the last one is a mitigation action. So the mitigation action is actually to try to fix the issue or try to do some mitigation steps. So that's the 3 types action our RC Copilot supports. Okay, so this is the example of the incident handler and their actions. So, for example, if the issue type is a busy hub, then we will narrow down our scope to a single server instead of a whole, forest or a DAG, right? So this is a scope switching action. And for the query action, basically, if it is a non-issue, then we will perform this get thread stack grouping .PowerShell, this kind of PowerShell script to collect the multimodal data. And for the mitigation action, we can see that we can either restart the service or we can engage other teams or report to a specific team. So basically, those kind of handlers or actions are reusable and also customizable. So reusable means each action will be stored in a database. So later, when you construct a new incident handlers, you can reuse those actions, or you can even reuse the incident handler again. And for customizability, it means that we can easily just delete one node from the incident handlers and substitute it with another node. So that is a customizable design for us. So that's for the incident-related information collection stage. And for the root cause prediction stage, basically, we try to construct the few shots chain of thought prompt automatically. So our core design here is just automatic few shot, chain of thought prompt design, prompt construction. So that's it. However, it is not that easy. And the input of this stage is that is actually the incident data we collect from the previous stage. And the output is the root cause category we want to predict, and also the root cause details, like the explanations returned from the large language model. Okay, so why do we want to use the chain of thoughts? Why we want to use this kind of few shots COT prompting? Basically, we feel like the COT prompting is a very natural fit in our context. So what is a COT prompting? So basically, you provide some manual, demonstrations in your prompt, like your question and also its rationale and also the answers. You provide several such kind of pairs or tuples in your prompt, and then it can guide the large language model to predict it better or to have a more precise, answer. So in our case, in our context, we feel like the historical incidents could just fit into the demonstrations, since we have all of the reasoning steps stored in our database as diagnostic information. And also we have our answer, like the root cause category label. So in that case, the chain of thoughts, we believe the chain of thought is a natural fit for our RCA Copilot. Okay, however, doing the automatic COT prompt construction is not that easy. The main bottleneck is actually the token limit, or the length of the incident information we collect from previous stage could be super long. So a single incident information collected by our first module could contain more than 1,000 tokens. And also there are hundreds of root cause categories in our email service team. So if we just choose one incident instance from this 100 root cause categories, there could be hundreds of examples. For each example, you could have more than 1,000 tokens. So we all know that the current GPT-4 or GPT 3.5 only have 4,000 tokens or 8,000 tokens, which is not enough for our context, right? So the solution provided by us is actually to do the similar incident retrieval and also the incident summarization. So the intuition behind the similar incident retrieval is that the on-call engineers also refer to the historical incidents to try to use it as a guidance for the incoming incidents. So in our case, we want to provide the examples for the large language model. So that's why we want to do the similar incident retrieval. However, the question here is how to measure the similarity, right? So in our study, we have derived the insight that the incidents stemming from the similar or identical root causes often recur within a short period. So the 93% of the recurring incidents tend to reappear within 20 days. So this time locality, makes us to come up with a new, formula. So this is the formula we use to try to calculate the similarity. So basically, we not only calculate the distance between the, two embedded incidents in the embedding space, but also we try to calculate the, the time, or the more specifically the date of the incidents to calculate the similarity. And also we use the fast text to do the embedding and store them in the embedding database. And for the incident summarization, the intuition is the same as the similar incident retrieval. Since the one single diagnostic information collected by the RCA Copilot, information collection stage is super long. It could contain more than 1,000 tokens. So we want to do a kind of summarization task first before we use the prompt to give it to the large language model, basically GPT. So we limit the number of words for the summarization, maybe 140 words. And the results has shown that the RCA Copilot can summarize those diagnosis information very well. As you can see that it extracts out the UTP socket count from the original diagnostic data. So the summarization can be done very well. So in that case, we are able to do the automatic chain of thoughts prompting. And so for this example, the demonstrations for this COT prompting is 3. So basically, we provide 3 choices for the large language model. The A and B are basically similar incidents in our database with the root cause label. And the option 3 is actually a non-option. It's basically a dummy option. Like if the large language model cannot believe, okay, A and B is a correct answer, their root cause is a correct answer for the incoming incident, then it will actually choose a C. So that is a chain of thought prompting for us. And also we ask our large model to provide the explanations for the incoming incidents. So for our evaluation, RCA Copilot is able to achieve 0.76 F1 scores when predicting the root cause category or root cause labels, and it overperform other baselines in our evaluation. And also we find out that the summarized diagnostic information is even more useful than the diagnostic info. So we infer that the reason behind that the original diagnostic information, though it's maybe 1,000 token, it could still mislead the larger model. So the summarized version is even better than the original diagnostic info from our first stage. And we have successfully deployed the RCA Copilot in several teams, maybe 30 or 40, I cannot remember. And the first module, the diagnostic information collection module, has been deployed over 4 years at Microsoft. So in conclusion, we propose the RCA Copilot, which is an automatic end-to-end solution for the cloud incident root cause analysis. You can regard it as a root cause analysis agent. And it can efficiently collect the incident-related diagnostic data, and also it integrates a large language model to predict the incident root cause categories with explanations. So that's all about this paper. I'm happy to take any questions. Yeah.
Yeah, thank you, Yifeng, for presenting such a wonderful work. Yeah, if any of the audience has any question, please raise your hand and unmute yourself. If not, yeah, go ahead.
I mean, so what should I say? Like, so basically, this area is related to the application of the large language model instead of the design or training or inference stages of the large language model. So I don't know whether you folks are working on the application perspective. Yeah. So I'm happy to discuss with anything from the audience. Yeah. And also, I may speak a little bit fast because I want to squeeze into 20 minutes. So yeah, if you are, you are not sure about some some components or some part of my presentation, feel free to ask. Yeah.
Cool. Qinghao, would you like to begin first, or I can start first? Okay, I'll just start first. To introduce some better questions, maybe. So on slide 10, you mentioned that they still require some predefined incidents handler, if I understand it, if my understanding is true. So would you say it possible? Do you think it would be possible if they deploy it with something like a long chain and let the LLM to fix the code altogether, or think of some solution by scanning the code base and to come up with some incident handler?
That's a very good questions. Actually, I skipped some details here. So basically, the predefined incident handlers are actually manually constructed by the, engineers. So the only manual work in our RCA Copilot is to manually build those incident handlers. And there are some following works in Microsoft, like they try to even automate this process. So by scanning the code base or by scanning even the troubleshooting get, can we automatically construct those incident handlers instead of manually do it? Yeah, so actually they have some following works. Yeah.
Yeah, wonderful. And in your evaluation, you talk about the summarized diagnostics are better than the full diagnostics. And I think that is a very good insight. Wonder whether with growing context window size, do you think it will help in the future work of this project? If you, let's say, can you put a million?
Actually, I don't know. Yeah, actually, I don't know. So when this work was done, maybe in March or April, like at that time, there is no 64K or 132K, those kind of models like can have a very huge input. So all we have is maybe 4K or 8K, models we can use. So that's why we have that kind of design. So currently, I believe, I haven't tested it, but I believe that those new models can do it better, even if we don't do this kind of summarizations. Yeah.
It remains to be tested. All right. Thank you. That's all my question.
Yeah,
Qinghao,
Hi, Ivan, can you hear me?
Yeah, I can hear you. Go ahead.
Very nice talk. I want to ask about the train of thought part. Have you implemented an other kind of strategy of prompt or
Yes, we have. So basically, if I don't know whether it's suitable to go to a paper, but anyway, I will just speak. Like we have tried other prompting or embedding, methods. First of all, so as I have introduced, like we use a fast text to do the embedding, but we have also used a GPT embedding. We found out that the GPT embedding is super slow. So for example, for here, no, not actually, not here, here. The GPT-4 embedding will actually takes maybe thousands of seconds to finish the embedding, task. So that's why we use the fast text. And for the prompting, actually, we have done this, like we never give the similar incidents. We never give the similar incident examples. We just feed the original diagnostic info to the, for example, here. We just feed the diagnostic info here. And we have also tried to feed other types of informations to see whether a prompt can lead to a better results. And also we have just, for example, we just provide the diagnostic info with a list of root cause labels. For example, there are hundreds of labels in our dataset, right? If we just provide this a list of labels with the diagnostic incident information, can we achieve a better results? Actually, the answer is no. Yeah, but I believe we didn't put it here. So yeah, we try different designs of our prompting, and we figure out that the current design is the best. Yeah.
Yeah, great. Do you do some fine tuning on the model? Adjust the
Yes, we have done fine tuning. Like there is a fine tuned GPT approach. Basically, this work is ICSE 2023 maybe. Yeah, so they try to use the fine tuning to predict the incidents. But in their work, they just give the explanation and then use a blue score to calculate the similarity between the text. But we apply their approach to our context to our context, and we find out that the result is very bad. As you can see, that the F1 score is just 0.1. So we try fine tune, but the result is not very ideal. Yeah, the reason behind it could be that like the training data is not so much, right? So fine tuning may not work that well. Yeah.
How about you said you will release the code. Have you released the code and the data set of this work?
Oh no, I never said I will release the code. Yeah. I
no.
don't have a property.
The data set also will not release.
It decided by the Microsoft. I think they are hesitating, like because those incidents are very sensitive.
Yeah,
It excludes a lot of companies internal information, so they are very hesitated to do that. And also, if you see my slides, the first slides or the background slides, I only show other companies' outages, right? I never show Microsoft's outage or incident news here. That is requested by them. They are very kind of strict. Yeah.
Yeah, I understand. Thank you.
Yeah, thanks. Okay, thanks. Do we have other questions from audience? We have another audience, right? Zerui or Ariana. Okay. Yeah. Zerui, do we have any question?
Go ahead.
I'm sorry, did you call me?
Yeah, I just wonder whether you have any questions.
Oh, I think it's a very nice talk. Like, yeah, and I don't have any like computer science background, so yeah, no questions.
Okay, fine. Yeah, thanks.
All right.
Zerui, do you have any question? Okay, yeah. Anyway, so feel free to ask any questions or drop an email to me if you have any ideas.
Yeah, E09 is in our group. And once again, thank you so much for presenting this. And we're looking forward to a future work like based on it. And thanks for your time.
Sure.
And thanks for
thanks a lot. Thanks, audience. Thanks, Qianhao. Yeah.
Bye.
Yeah, bye.
See you next time. Bye-bye.